Okay, hello everyone, and welcome to our second class. And today we'll be covering all you need to know for these concepts, like for circles and 3D dimensional geometry. And they are seen very oftenly on these competitions, especially the AMC 10. And we have given that competition more priority right now since it's about to happen. So let's go over some basics, since there might be some people who don't know the basics. So this is a picture of a circle, and the circumference is just the length. It's just like the perimeter, and it's calculated as 2 pi r, where r is the radius. And if you don't know what the radius is, then the radius is just half of the diameter, and it's taken, if you take a point, like pretend this is the center, and if I draw this line to anywhere on the circumference, these are all radiuses of this circle. And the diameter is just, if I stretch it all the way out, that's the diameter. And this is what it says. And now we're going to use this information to solve some basic problems that you guys shouldn't have a hard time with, but if you do, that's perfectly fine. So circles of radius 2 and 3 are externally tangent and are circumscribed by a third circle as shown in the figure. Find the area of the shaded region. So this is just, we have to find the area of the shaded region, which means we need to find the area of the bigger circle, and then we subtract the area of the two smaller circles. So first, to find the area of the circle, the bigger one, we know that what the formula is. It's just pi r squared. Now, remember, the radius is half of the diameter, so we have to find the diameter. So if you make this point go all the way to this to the circumference here, and the radius is 2, that means this length is just 4. And if this length is 3, and you connect this all the way here, then this length is 3. Now if you add all of these numbers up, you get 3 plus 3 plus 2 plus 2, which is equal to 10. That means the diameter of the bigger circle is just 10. And remember, the radius is half of that diameter, so the radius is 5. So you substitute 5 into the radius, and you get 5 to the power of 2, which is just 25 pi. That means the area of the whole circle is 25 pi. Now to find the shaded region, now we're going to subtract the two smaller circles. And it says the radiuses are 2 and 3. So if you substitute this into the formula pi r squared, the radius 3 goes in. So 3 times 3 is 9, times pi is 9 pi, and 2 times 2 is 4 pi, you multiply by pi because the formula of the area of the circle is just pi r squared, and you get 4 pi, which means the area of these two regions, these two circles combined, is 9 pi plus 4 pi, which is just 13 pi. Now to find the area of the entire region, we have to subtract it from the entire region, which is 25 pi minus 13 pi, which is just 12 pi. So now this is our next problem. I'm going to give you guys some time to solve it, about a minute, and you'll get close to the algebraic equation for this problem. So I'll read it out and you can solve it on paper. So a circle of radius 2 is centered at O. Square OABC has side length of 1. Sides AB and CB are extended past B to meet the circle at D and E, respectively. What is the area of the shaded region in the figure, which is bounded by BD, BE, and the minor arc connecting D and E? I want you guys to take try this problem. Well, I'm just gonna draw some shapes inside and there are two figures, because we're going to use both of the figures so the diagram doesn't get complicated. I'm just going to draw stuff inside while you guys try the problem. Okay, now while you guys solve this problem, I'm going to tell you guys the steps for this problem. Later on, when we have more problems that are going to go more into the depths of these concepts, I'll give you guys more time to solve those. But these are some basic problems, because if we solve these problems and learn the concepts, then it's going to be a bit easier to solve the harder ones. So we're going to solve these basic ones first. So I just drew the point D all the way to point O, which is the center of the circle. And then that's just the radius of the circle, because that's from the center to the circumference. So DO is just 2. Now, it says that the square has a side length of 1. So we know this is 1. Now, if you remember from our last week's class, we're going to use the Pythagorean theorem, because this is 90 degrees, because it shares the same angle as a square, and we know that a square has a 90-degree angle. So if this is 90 degrees, we can find out dA, which is just 2 squared equals to 1 squared plus dA squared. Now this is just 4 equals to 1 plus dA squared, which is equivalent to 3 equals to dA squared. And then to find dA, you just square root both sides, so you get dA equals to the square root of 3. And it's the same story here for triangle COF. Because you know, the hypotenuse is 2 and the other side length is 1. So this is OF is also the square root of 3. Now to find DOE, we know that is just an arc we have to find. And we need to know the angle measure of the arc. But then, if you remember from last week's class, do you know what triangle this is? It's just a 30, 60, 90 triangle, because you know 1, 2, and the square root of 3. So the opposite of square root of, the opposite of the 30-degree angle, pretend that's 1. That means the opposite of the 90-degree angle is just 2 times that, and we just see that through the triangle. And the opposite, the 60-degree angle is just square root of 3 times the 30-degree angle. So this is also 60 degrees. And now we're going to use this information to try to find out the area of the arc. So I'm going to erase this triangle, and I'm going to redraw something. We're going to connect these lines. And then we know this is 90. Now, I want you guys to try this problem now, since I told you guys the angles and the 30, 60, 90 relationship in this problem. Oh wait, oops, I accidentally made a mistake here. I forgot to, I'm very sorry, I apologize. I actually meant, no, I actually meant OFE. Sorry, I meant this yeah, I meant this triangle here. Sorry, I accidentally drew the wrong triangle. So, we know that the whole height of DA is just the square root of 3. I'm going to redraw this so it's a bit cleaner. So we know DA is the square root of 3, and we know BA is 1. So what is DB? It's just square root of 3 minus 1. Now we're going to connect DO and EO. And this side length is 2 because that's the radius, and this is 2. So I'm going to give you guys like 1 minute to solve this problem. Oh wait, some people I think are confused. So basically we also have to divide this triangle. Okay, they want me to redraw it. This angle is 30 degrees based on, because we know that if this is 30 and this is 30 because of the 30, 60, 90 relationship, then 90 minus 2 times 30 is just 30 degrees. So this is 30 degrees. So now if that's 30 degrees, that is just 1/12 of the area of the entire circle. So if it's 1/12 of the area of the entire circle, what is it? Pi r squared, and the radius is 2. So it's 4 pi. So that means the area of the sector is just pi over 3. Now I want you to solve this problem. Oh, by the way, when I say arc, I mean ODE. When I said arc, I mean ODE. We found the area of ODE as pi over 3. Now we just have to subtract the triangles, and I want you guys to do that. So it's some computation. Okay, so I'm gonna tell you guys the solution to this problem. Basically, if you take triangle DBO, you know this is the base, it goes like this. This is the triangle. So you see, if this is the base, then the height is just this length, and that is the square in this case. Do you see it? So the height is just 1. And the base, as I said, is just square root of 3 minus 1. So that is the side length the base of the other triangle. So if you use the formula for this triangle, it's just square root of 3 minus 1 times 1 divided by 2, because base times height over 2. And if you use that formula, you get square root of 3 minus 1 divided by 2, which is the area of one of the triangles. But we have two of those triangles since they're both congruent. So we remove that fraction because 1 over 2 times 2 is just 1. So it's just square root of 3 minus 1. However, we have to subtract it from the area of the arc, DOE. And that is square root of, that is, wait a sec. That's pi over 3 minus square root of 3 plus 1. And that is the answer to this problem. So you see, we found the answer by just making triangles inside, which is why we covered the triangles class first, because circles are a lot about triangles. So now we're going to go over to the next problem. So I want you guys to solve this problem. I'm going to read it. I'm going to give you guys like a minute. So a circle of radius 1 is tangent to a circle of radius 2. The sides of triangle ABC are tangent to the circles as shown, and the sides AB and AC are congruent. What is the area of triangle ABC? I want you guys to solve this. Okay, whenever you see a problem which involves tangent points, I'm going to tell you what to do. You always connect the center to the tangent point. And whenever you do that, whenever you connect the center and make a radius to the tangent point, you're always going to make a 90-degree angle. So let's do that here. If we connect this to the tangent point, as I said, this is 90. And if you do this here, this is 90. Now I'm going to make a whole segment from the top to the bottom. I don't know if you guys see this or not, but to me this looks like similar triangles. So now we're just going to use similar triangles and triangle ratios. So basically, if this is the radius of the circle, of the bigger one, this is 2. And this is the radius of the smaller circle, which is 1. So what do we know about these two triangles? Pretend I'm gonna give them some side lengths. Pretend this is D, and this is E, and this is F. I'm so sorry if it's a bit messy. Using these ratios, we know that the other triangle on the top, AED, has segments that are half of the AFG triangle. So using that, we know pretend this is X. So the hypotenuse of AED is X plus 1, and the hypotenuse of AFG is X plus 1 plus 1 plus 2, which is X plus 4, and it has to be as the same ratio as the base lengths, so 1 over 2. Now this is just some simple algebraic equations. You multiply both sides by 2, you get 2x plus 2. Now I'm going to multiply both sides by x plus 4 to remove x plus 4 here and bring it over here, which equals to x plus 4. And if you solve this equation, you get x equals to 2. So which means this value is just 2 simply. Now, okay, I'm gonna make it neater. So we have 2 over here now. So we know if the base length of this triangle is 1 and the base length of the other triangle, I mean the hypotenuse is 3, we can use the Pythagorean theorem. So 3 squared, which is the length of the hypotenuse, minus 1 squared equals to AD squared. And this simplifies to 8 equals to AD squared. And then you square root both sides and you get AD is just 2 times the square root of 2. And now, using this information, I want you guys to find the area of ABC. So I'm going to give you guys some minutes, some time. Okay, this is a basic problem, so I'm going to go over this a little bit. I'm going to go over the problem like right now quickly. So basically, now we're going to use similar triangles. Pretend this point is just H. So we know that AHC is just similar to the other triangle, this one. I'll laser this one. It's similar to that. So now we're going to use ratios to find out the length. So the hypotenuse, not the hypotenuse, we're going to use the base of the, the height of this triangle, which is just 2 plus 2 plus 4, which is 8. And the height of the other smaller triangle, which is 2 square root of 2. Now we want this to be the same ratio as the base, and the base of the other triangle, the smaller one, is 1, and the base of this triangle is just HC. Now, do you see what we're going to do? We're going to multiply both sides by HC, and we get 2 times the square root of 2 times HC equals to 8. Now, all we have to do is divide both sides by 2 square root of 2. So I'm going to erase this and to make some space since there's a lot of competition. So 8 divided by 2 square root of 2 is the length of HC. Now, the length of BC is just times 2 of this, which cancels out the 2, which is 8 over the square root of 2. But we're gonna rationalize this because most of these problems involve rationalizing. So you multiply square root of 2 to both sides and you get 8 times square root of 2, and square root of 2 times square root of 2 is just 2, and you cancel out the 2, and you get 4. So the base is 4 square root of 2, and the height is 8. So we're just gonna use the triangle area formula, which is 1 over 2 times 8 times 4 over 2. And 8 times 1 over 2 is just 4. So 4 times 4 over 2. And then you get your answer, which is 16 square root of 2. Okay, so what do you guys have any questions? No, I agree, it might look like it's a lot of competition, but it's all about similar triangles. If you're still a bit confused, I can understand, because sometimes when people start competition math and these concepts, it can be a bit complicated for them. So if it's still complicated, I recommend checking out our last class since it explains all the concepts for similar triangles. So after this class, I recommend checking that out. Okay, so someone's asking how we got the similar triangles, which is a good question. I should have explained that. So because, angle HAC is used in triangle HAC. And, and we use angle-angle similarity. All 3 of these triangles, they're right triangles, but they all have this angle in common. This one, this angle. Do you see this angle that I'm highlighting over here? This angle is in common, which is how we got similar triangles. Now we're going to move on to the next problem. This is a nice problem. Many Gothic cathedrals have windows with a portion containing a ring of congruent circles that are circumscribed by a larger circle. In the figure shown, the number of the smaller circles is 4. What is the ratio of the sum of the areas of the 4 smaller circles to the area of the larger circle? This is a nice problem, and I want you guys to try it out. And I'm going to give you guys a hint. whenever you see a ratio problem, remember, if you give the side length, the radius or side length of the shape 1 billion or 1 or 0.1, the ratio will always be the same. So instead of like substituting variables and making it a complicated expression, maybe put in some numbers. I'm just going to draw some figures inside to give you guys some hints. So, obviously, whenever you see circles, you need to connect their centers, usually, and then you might see some patterns. So you connect the centers. Now, we're going to pretend the radius of the smaller circle is just 1. So pretend this is just 1, because we could add it as x, but it's just asking for the ratio, so we can substitute 1. That's the best part about ratios. So this is also 1. Now, do you notice something? We want to find out this length here. I'm going to highlight it. This length. Maybe you might not see this, but after some practice, you will always see the pattern. This is just the Pythagorean theorem, since this is a 90-degree angle. And then, we know the side length is just 2, because it's 2 radii, so 1 plus 1 is 2. This is also 2. And then, using the Pythagorean theorem, 2 squared plus 2 squared, which is 4 plus 4, 8. 8 equals to, pretend this length is x. So x squared, and then you square root both sides, and you get 2 square root of 2. And yes, you can also use 45, 45, 90 triangles, but not everyone remembers those pairs. But this is 2 square root of 2. Now, we got the diameter of the bigger circle. We're going to get the radius soon. So, what is the area of one of the smaller circles? It's just pi r squared. And then the radius is 1. So it's just pi, 1 squared, and 1 squared is just 1. So 4, and so it's pi, and we have 4. So 4 circles, which is 4 pi. And the larger circle is simply just, it's 2 square root of 2 plus 2. That is the diameter. So the radius is just square root of 2 plus 1. So it's pi r squared, which is square root of 2 plus 1. And if you simplify this, you get pi square root of 2 times square root of 2 is just 2. 1 times 1 is just 1. And 2 times the square root of 2 times 1 is 2 square root of 2. So this simplifies to 3 pi plus 2 pi times the square root of 2. Now the pi's just cancel out. So at the end, you get 4 over 3 plus 2 square root of 2. But remember, this is the AMC 10 or AMC 8. These problems, you need to rationalize the denominator. So you rationalize it by just multiplying the bottom thing again, but the opposite symbol. So if you multiply it by 3 minus square root of 2 square root of 2. So that's the answer. So now let's go over some concepts. So tangency. Well, tangency is just one point of intersection. It's like basically you're touching the shape. For example, a circle will only have one tangent point with one line. The number will be more if there are more lines. That's obvious. And then if you add more lines, the number will increase. Usually when you see a problem involving tangency, all you have to do is connect the center to the tangent point. Not all, but that's a very important tip. You connect the center to the tangent point, which is a very common technique. And at the end of the day, remember, circles are all about drawing. Now, there is one important theorem. If two tangent lines of a circle meet at the same point, then both of the segments are congruent. So you connect the point to the tangent point. And here, you see they're both tangent and they meet at the same point. That means these two segments are congruent. This is a very commonly used theorem, and it can actually help you find some very hard problems very easily. This is a very nice problem that involves the tangent point theorem. I want you guys to solve this. I'm going to read it, and I want you guys to solve it. Square ABCD has a side length of 2. A semicircle with a diameter of A from C intersects AD at E. What is the length of CE? I want you guys to solve this problem, but I'm going to give you guys a tip. Use the tangent point theorem. Remember, if two tangent lines meet at the same point and they're tangent, then those segments are congruent. Now, using that technique, I want you guys to solve this problem. Okay, I'm gonna draw some figures inside, not figures, but lines. Remember what I said? You connect the center to the tangent point. As it says, CE is tangent. So you connect this to CE. Now, if you notice, pretend this is F. Do you notice the pattern? So C is the common intersection point. CB and CF are both tangent to the circle, the semicircle, same thing, but it meets at the same point, which means CF equals to CB, and CB is just 2 because it's the side length of the square, which means CF is 2. Now we're going to look at this other shape. Pretend this is a G. So if you look at the shape AEFG, do you notice what we have to do? Well, if you notice again, EF and EA are tangent to the circle again. We use the tangent point theorem, and we know EA equals to EF. We don't have the side lengths, so now we're going to use some variables. This is X, and this is X. This is also 2. We know DC is 2. It's the side length of the square. So what is DE? DE is just DA minus EA, which is 2 minus X. Now we got some Pythagorean relationships. This is a 90-degree angle. Now we can find X easily, and then add it to 2, and we get the answer. So 2 squared plus 2 minus X squared equals to 2 plus X squared. Now this is just some simple computation. So 4 plus X squared minus 4X equals to X squared plus 4X plus 4. Now, the X squares just cancel out, because if you subtract X squares from both sides, it's just going to become 0. And then you see the 4X, you add 4X to both sides, you get 8X here equals to 4 plus 4 is 8 minus 4 is 4. So you divide both sides by 8, and you get X equals to 4 over 8, which equals to 1 over 2. Now, if X equals to 1 over 2, we just get 2 plus 1 over 2. Because CE, we know CF is 2 and EF is 1 over 2. So the answer is just 2 plus 0.5, which is 2.5 or 5 over 2. Both work. Both are the answers. So you see how important that theorem is? Well, this is a nice problem. I drew the diagram in here because this problem, if I draw it with my hands, it's going to be messy. So I had to use the picture. So circles A, B, and C each have a radius of 1. Circles A and B share 1 point of tangency. Circle C has a point of tangency with the midpoint of AB. What is the area inside circle C but outside circle A and circle B? So remember, circles are all about triangles inside, because in many of the problems you draw triangles and you subtract areas and then you just get the area after. So in this problem, I got this picture from before because if I draw it, it's gonna look messy. So if you look at it, this shape, so this arc here, we notice this is just a 90-degree angle. So what does this mean? And we know the radius is 1 and 1. So what is the area of the entire circle? Circle B. It's just pi. And what is the area of this arc? It's just 1/4 of that. So pi over 4. Now we want the area of this triangle, which has side lengths of 1. So 1 over 2 times 1 times 1, which equals to 1 over 2. So the area of half of this region is just pi over 4 minus 1 over 2. However, we have 4 of these regions, because you see here, we have 4 more. So we just multiply this by 4, and you get pi minus 2. Now that is the area of the region that is intersected. And now we subtract this from the area of the entire circle. And the area of circle C is just pi r squared, but the radius is 1. So the area of the circle is pi. So you subtract pi minus 2. You get pi minus pi plus 2. The pi's cancel out, and the answer is 2. So you see, circles are a lot about triangles. This is a nice problem. I'm going to read it out, and I want you guys to try it. So circles with centers O and P have radii 2 and 4 respectively, and are externally tangent points A and B on the circle with center O and points C and D on the circle with center P, such that AD and BC are common external tangents to the circles. What is the area of the concave hexagon AOB-CPD? I want you guys to try this problem out. Okay, so I'm gonna give you guys some tips. Remember that tangent theorem that I just showed a few minutes ago? Well, pretend I extend DA all the way here, and I extend BC all the way here. Sorry, it's a bit messy, but pretend I get these two triangles. We know what if this is like F. DF is congruent to CF. We can actually just use similar triangles, because if I connect this height here, these two triangles are just clearly similar, because this angle AFO are common in both of the triangles. So we know DP is 4. What is AO? 2. Now what is PO? It's just 4 plus 2, 6. So now using that information, let's pretend FO is just X. The whole thing, FO. That means the ratio of x over 2, the hypotenuse over the base, is the same as the entire hypotenuse, which is x plus 6 over 4. Now we solve this equation, and we get 4x equals to 2 times x plus 6, 2x plus 12. Now you subtract 2x from both sides, and you get 2x equals to 12, and x equals to 6. So now we have x is equivalent to 6 over here. And now, this is 4. And because this is 2, we have to subtract that. Now I want you guys to solve this problem. Okay, now this is just easy. I'm gonna solve it out because... So now we know that FDP, we want AODP. It's just the area of the bigger circle, the bigger triangle, minus the area of the smaller triangle. We know that the height of the smaller triangle is 6, times 2 is the base. Not 6, we have to find out that's the hypotenuse. I'm very sorry, I apologize. So if we use the Pythagorean theorem, we have 36 minus 4. Because the height is 6, you subtract 2. 2 squared, 4. You get equals to 32, and then you square root 32, and you get 4 square root of 2. Also, you could compute this out using similar triangles and ratios. However, we know that the segment FD is exactly double FA. So we're not going to compute it out. We're just going to write this is 4 square root of 2, and the whole segment is 8 square root of 2. So now, the area of the bigger triangle. Now I'm going to erase this and rewrite it. So the area of the bigger triangle, which is 1 over 2 times 4 times 8 square root of 2, which is, this becomes 2, which is 16 square root of 2, minus FAO, the triangle FAO. The segments are 1 over 2 times 4 square root of 2. However, these twos just cancel out. We get 4 square root of 2. So before you box out 12 square root of 2, remember that this is the area of AODP, which is half of the entire area that we want. So that means the area of the entire thing is just 2 times that, which is 24 square root of 2. And we're done. The next problem. Yeah, this is a very nice problem. I'm going to read it out and give you some time to solve this. I want you guys to solve this. It's a wonderful problem. Circles of radii 5, 5, 8, and m over n are mutually externally tangent, where m and n are relatively prime positive integers. Find m plus n. So I want you guys to solve this problem. I drew the figure before because it's going to take a long time to draw this figure with a neat shape. So now the figure is there. I want you guys to solve this problem. Okay, I know this problem might be a bit hard, so I'm just gonna draw out a bit. Draw some things out. So we know that this is just the radius of the circle. So this is also 8. And what is the radius of the bigger circle? I mean the smaller circle, it's just 5. So if you draw this length here, continue it down here. Pretend we don't know this the length of that. But we know this is a 90-degree angle. And this is 13. The hypotenuse is 13. So now we need the height of the triangle. I'm just going to solve a bit of the problem and leave the rest on to you guys. So 13 squared minus 5 squared equals to, d squared. Pretend d is the height. I mean, maybe you don't know the 5, 12, 13 triangle pair. And if you don't, that's perfectly fine. Then you can just use the Pythagorean theorem. And if you subtract this out, you get 144. And then you square root that, and you get the height is 12. Now I want you guys to solve this problem. Yeah, if you guys are finding these problems a bit easy, that's because these concepts are easy for you. And even though these are from like the problems I found out were considered very hard on the AMC 10. So if you're able to solve these easily, that means you know these concepts well. So just wait, since the problems we're going to get in later on towards the end will be very hard. And if you're able to solve those and understand, then you're fully ready for the AMC 10 circle problems and 3D dimension. Yeah, so a lot of geometry problems, the goal is to turn it into an algebra problem. We know the height of this point. I'm going to laser this point over here. I'm gonna this point. So if the height of the whole thing is 12, we know the radius is 8. So that means r plus whatever this blast segment is. I don't care what it is. It's random. It's just 4 minus r, because the whole thing is 4. You subtract r, 4 minus r. So if it is 4 minus r is that, and we want the hypotenuse. We know part of it is just 5 from the radius, but there's another circle that goes through, so it's the radius of that also. So we're gonna make an equation now, the Pythagorean relationship. So 5 plus r squared, that is the hypotenuse, equals to 5 squared, which is 5 times 5, which is 25, plus 4 minus r squared. Now if you solve this out, you get r squared plus 10r plus 25 equals to 25 plus r squared minus 8r plus 16. Now, this is just some simple computation. You notice that the r squares just cancel out. The 25s also cancel out. And then you add 8r to both sides. You get 18r equals to 16. And then you divide 18 from both sides, and you get r equals to 16 over 18. And you reduce this, and you get 8 over 9. Oh, not 8 over 9, sorry. We have to read the problem. We have to find m plus n. So 8 plus 9 is just 17. Remember, 0 and 17. Because on the AAME, you have to write 0 with it. So remember that part. That is a very important thing to remember. So we turned this complicated looking problem into a very simple problem, which just became algebra. Simple algebra. One equation, one variable. And now we're going to solve some more problems. Now, the diagram shows 20 congruent circles arranged in 3 rows and enclosed in a rectangle. The circles are tangent to one another and to the sides of the rectangle as shown in the diagram. The ratio of the longer dimension of the triangle to the shorter dimension can be written as 1 over 2 times the square root of p minus q, where p and q are positive integers. Find p plus q. Also, if you guys are finding these problems easy, that's a very good thing. That means you guys are almost close to mastering these concepts, which means for this year's AMC 10, you will be prepared for their circle problems 100% guaranteed. Remember, with a lot of circles, don't be frightened. Remember, you connect the centers. And as I said before, if it's a ratio problem, don't write variables. Not always. You can just write some random number. Even 1 billion, that's too big. Just write 1. So we're going to use that information. And remember, we need a triangle. Not just a triangle, a right triangle. So I'm just going to connect some centers and test it out and see if I get something. And then I get this triangle. And using this, we're going to try to solve the problem. So pretend the radius of one circle is just 1. That means the radius of all of the circles is just 1 because they're all congruent, 20 congruent circles. So we know this is 2 because it's the diameter. The diameter is 2 times the radius. So this is 2. And this is 1 because it's a radius. What is the base? 1 plus 1, which is 2. And we want the height of this triangle, of the rectangle. So if you use the Pythagorean theorem, you get 4 squared minus 2 squared. Pretend the segment is just x. So you get x squared. And if you simplify this out, you get x squared equals to 12. And then using this, you square root both sides, and you get x equals to 2 square root of 3. And we're almost close to our answer now. That is not the height of the triangle, the rectangle, because you also have to add 1 of this and 1 of this, which is 2 radii, which is 1 plus 1, 2. And the height of the triangle is already 2 square root of 3. So what is the height? So we want to find the ratio of the longer dimension to the shorter dimension. So the shorter dimension is just 2 plus 2 square root of 3. Now, how are we going to find the length of the rectangle? Well, if you see this thing, then you will just get it in 1 second. The length of the rectangle is just, if you connect this whole thing, it's just the diameters of 7 of these circles. We know the radius is 1, the diameter is just 2, and there's 7 of these circles. So 2 times 7 is 14. Divided by 2 plus 2 square root of 3. Now you divide 2 from both sides, and you get 7 over 1 plus the square root of 3. Now I want you guys to try to solve this problem now. It's just some computation, but it's good practice, in my opinion. Oh, remember to rationalize the denominator. So if you rationalize the denominator, you get... No, I'm gonna flip this over. I'm gonna write square root of 3 plus 1. It's always better to have the radical sign first. Now try to rationalize it. So you just multiply by square root of 3 minus 1 over square root of 3 minus 1, and you get 7 square root of 3 minus 7, and square root of 3 times square root of 3 is 3 minus 1, 2. So now, do you see this? The 1 over 2 comes from the 2 here. So that means the square root of p minus q equals to 7 square root of 3 minus 7. So we have to rewrite this in terms of just one number, which is under the radical. And that is done by squaring the integer that is outside of the radical sign, which is 7 squared, which is 49, times the number inside times 3. You simply get 147. So this is just square root of 147 minus 7. But we want the sum of these integers, 147 plus 7. That is 154. Do you guys have any questions? Yeah, okay, so do you guys, if you have any questions, please write them in the chat. Okay, I'm gonna go, to the next problem. Not next problem, I mean the next concept, which brings in power of a point. Well, if you think a point is just a random dot, no, you're wrong. All points are powerful in mathematics. And you get ready to learn some very powerful theorems. And we're going to do a very hard problem, but with power of a point, it's very easy. So a secant is just a line that goes through a circle and intersects it at exactly 2 points. So, do you see this? It goes through 2 points of the circle. It's a secant. And then a radius, I just went over that in the beginning of the video. A chord is just this segment to this like 2 points and inside, but it does not go outside. A secant can go outside the circle, but a chord does not. A tangent line, as I said before, it just intersects at 1 point of the circle. If there's one tangent line, just 1 point. So now we're going to go over some relationships of power of a point. So if a tangent of a circle and a secant form a point, then there will be this relationship all the time. So pretend we have tangent AB and secant BD. I'm very sorry if I can't pronounce it. So basically, they meet at the same point. We see they meet at B, point B. So the relationship that we make is the tangent, the length of the tangent squared equals to the length of the line, whatever, secant or whatever. I'm just gonna call it S. So BC, because this is outside the circle, the length that is outside the circle times the entire line, which is the SECANT. And then if two SECANTs form a point, if two of these form a point, then there's this relationship. So CB, the length that is outside the SECANT, CB times the entire line, I'm just going to call it S from now, CB times AC, which is equivalent to the length that is outside, again, CD times the whole line. This is a very powerful theorem, and I forgot to name one thing. If there are two chords, pretend I have chord AB and chord CD. Then this theorem states that pretend this they meet at E, then CE times DE equals to AE times BE. Also, for those who want a proof for power of a point, we cannot go over it right now because it's a very long proof. However, you can test it out on your own. It's related to similar triangles. Maybe draw out some similar triangles and maybe you'll see it later. But the proof is very long, so we can't go on it right now. Not similar triangles, but like there's a lot of drawing and a lot of theorems involved. We don't have enough time to go over it right now. So now it's time. We'll do the raffle later because I haven't made the form yet. I forgot. But so if you're getting these problems wrong, just remember that Albert Einstein said, "A person who never made a mistake never tried anything new." I'm telling you guys this because some people were very discouraged during our last class because they were making mistakes. So I just want to say that don't worry, you'll learn it. That's why we have these classes to train you guys. Yeah, so just don't worry. You'll learn these concepts. Just take off. We'll have the break later because I haven't made the form yet. But we're going to solve a very interesting problem using power of a point, which comes from the 2013 AMC 10A. This is a very hard problem, but with power of a point, it's just simple computation. In triangle ABC, we have AB equals to 86 and AC equals to 97. A circle with center A and radius AB intersect at BC at points B and X. Moreover, BX and CX have integer lengths. What is BC? I want you guys to try this problem. It's a very nice problem and it has a very elegant solution. It can be kind of hard and a lot of computation, but with power of a point, it's very easy. Try this problem while I draw the diagram on the board. Yeah, just try the problem. I'm going to draw the diagram. Yeah, this is a very nice problem. I think it's one of the best problems that I've ever done from the AMC 10 because it shows how powerful power of a point is. This problem can be actually very complicated, but power of a point is very simple. Okay, I'm just gonna wait for someone to find out something quickly. Okay, I'm asking you guys to write your ideas down in the chat related to power of a point, or do you have any ideas about what to do? I want you guys to write them in the chat. Oh, someone is asking how to draw this problem. Well, basically first read the problem and it says radius AB, and AB is also side length of the triangle. That's why I drew AB as the radius, because that's what it says. That's why before drawing, I actually recommend reading it and then drawing it. That's why I read it first and then drew it. So we have AB equals to 86. I don't think someone has an idea about what to do right now, but that's perfectly fine. So in this problem, we have a triangle and AC is 97. Now, using power of a point, I mean not power of a point yet, but pretend this segment, this point here is F. What is AF? That's just the radius, because A is the center of the circle. So AF is 86, and what is CF? 97 minus 86, which is 11. And then if you use this, the theorem, you know, we can't just use this random line. We have to extend, because the S line, the SECANT, that line, it has to go to the end of the circle. So we're gonna make it go exactly to the tip here. Well, this means that it's CF, the segment that is outside, times, pretend this is G, times CG, times CG, equals to, I'm not going to write that down, I want you guys to try to find this now. Okay. Okay, it's fine. I think people are confused with this, but that's perfectly fine. All we have to do is pretend this point is H. So power of a point tells us that CF times CG is CH, the length outside, times the entire segment, which is CB, times CB. Now using this theorem, what is CF? We got that, that's 11. And what is CG? That is 86 plus 86, because it's the diameter, and 86 plus 86 is just 172 plus 11, which is 183. So it's 11 times 183 equals to CH times CB. Now, the way to do this problem is you find the factorization of 183, which is 11. We have 11 here times 3 times 61. Now all we have to do in this problem is use the triangle inequality, which states that two sides, if you add two sides of a triangle, it's supposed to be greater than the third side. So pretend I say this is, I'm just gonna use this randomly. So we know that the whole length of this triangle is 97. One length is 97, the other is 86. Pretend CB is 3. That is not possible. 86 plus 3 is not greater than 3. That is not possible. If you say 11, that is not possible. 86 plus 11 cannot be equal to 97. It has to be greater than 97. So then, the only things that seem possible are 33 and 61. And if you use that theorem, wait, yeah, because you have to remember the triangle inequality, which states that the segment has to be greater. So if this is 33, this is 28, and at the end the sum is always going to be 61. The bigger length is 61, so we know that CB is the bigger length. It can't be the smaller length, so it's 61. If you have any questions, please ask them in the chat right now. Yeah, before we move on to the next problem, ask some questions if you guys have any, and I'll try to answer them. But I hope you see that power of a point is a very powerful theorem, and using that theorem, this problem was just very simple. Okay, it seems like no one has any problems, so we're gonna move on. This is a nice problem, but it's kind of it might be easy for most of you. Oh, someone has a problem. So how did you get 61? Well, the reason is that after you factor it out, we know that CH times CB has to be 11 times 183, which is the same as 11 times 3 times 61. And then you know it can't be 3, it can't be 11. And then we get 33 and 61. But CB is the sum, and the sum is always 61. That's how we got 61. It has to be the bigger length. So, sorry, I'm gonna go back to the problem. So, a circle with diameter PQ of length 10 is internally tangent to P to a circle of radius 20. Square ABCD is constructed with A and B on the larger circle. CD is tangent to at Q with the smaller circle, and then the smaller circle is outside ABCD, the square. The length of AB can be written in the form m plus the square root of n. So now all we have to do in this problem is find the sum of m and n. I'm going to give you guys 2 minutes to try to solve this problem. It's a very nice problem. Okay, remember, there are circles and it says tangent point, and we want to find the length of AB. So I'm just going to label some stuff for you guys. This is 10, and pretend the center of the bigger circle is here, and it's A. I mean, not A is already used, so D is E. So I'm going to pretend the center of the circle is E. Then we know that this length is 10 because that's the radius. PE is just one of the radiuses of the circle, which is 10 plus 10, 20, and that's what it says, 20 radius. That's how I got this is QE is 10 because of 20 minus 10. Now, we need to find the length of AB. This problem is pretty simple if you actually look at it, because if you see, if this is the center, and we have this point here, A, and if you connect that point to A, and then you connect B to E also, these are also 20, sorry, because they're also radiuses of the circle. The radiuses of the circle, and also diagonals of the square. And then I see some Pythagorean relationships. Do you guys also see them now? Well, I want you guys to try this problem from now. Yeah. Oh, wait, I accidentally made a mistake here. Wait, I think I made a mistake. Wait. Length of... Yeah, now try this problem. Yeah, I'm gonna give you guys some time to solve this problem. It's a nice problem. It has a nice... It's all about drawing. Okay, now we're going to go over the solution to this problem. So basically, the solution to this problem is, I'm going to redraw this shape to make it look a bit neater and easier to understand. Pretend the center of the circle is here. I'm going to call it O. And OA is just one of the radii of the bigger circle, which has 20. Then, if you connect this segment, the center all the way to the end, we get a 90-degree angle. And when we see a 90-degree angle, we think Pythagorean relationships, Pythagorean theorem. Now I want you guys to solve this problem. Okay, it seems like no one has gotten the answer yet, but it's fine, I'll give you guys some more time. Also, we know that OQ is 10. Now try solving it. Maybe now it's a bit easier. And that means this is also... Oh, no, we don't know this length yet, but now I want you guys to solve it. Okay, now I'm gonna start labeling stuff because now I've given you guys enough time. It's fine if you don't get it. So we know that OE is just AB minus OQ. What is AB? We don't know what AB is. I'm gonna say it's X. And we know what OQ is, that's 10. Which means OE is just X minus 10. Pretend like AB equals to X. And the other leg, the AE, it's just half AB. You can see that clearly. This is just half of AB, so it's X over 2. Now we use the Pythagorean theorem. No, I'm going to say that AB is 2x, so it's easier to work with it. So this is x, and then this is 2x minus 10. It's going to be a bit easier, so less, so no fractions. So now we just use the Pythagorean theorem, and we get x squared plus 2x minus 10 squared, which is 4x squared, minus 40x plus 100 equals to 400, which is the 20 squared, which is the hypotenuse. Now, we just have to solve this equation now. I think we're going to use the quadratic formula. So we know x squared plus 4x squared. This is just 5x squared. Now what is minus 40x? I mean, that's just minus 40x. Now you subtract 400 from both sides and you get minus 300. All of these numbers are divisible by 5. We're going to reduce this equation. X squared minus 8x minus 60. Now all we have to do is put this in the Pythagorean theorem, and we'll get the answer after. Oh, I actually forgot one thing. No, never mind. Yeah, this is the equation we have. And if you put this in the Pythagorean theorem, you get 8 plus minus square root of b squared, because this is the term b, this is a, and this is c. So negative b plus minus square root of b squared, so 64. Negative 8 squared is just 64. Minus 4ac, the minus signs become plus 240 divided by 2a. 2 times 1, the coefficient is just 1. So 8. I'm going to erase the other, we don't need this anymore. So 8 plus minus square root of 306, 304 over 2. Now after solving, but this is half of the whole length, because remember, AB was 2x, and this is just x equals 2. What does this mean? 2x is just 2 times this, which means if you multiply both sides by 2, you get the actual length of AB. So which means the actual length of AB is just 8 plus minus the square root of 304. And that is the term we want. But all we have to do is add these integers. 304 plus 8, that's simply just 312. And that is our final answer. Well, unfortunately, there's one bad thing. There are really no theorems for 3D dimensional problems. However, there are ways you can find, you can memorize the ways to find the surface area and volumes. However, there are tricks that you can use. In a 3D dimensional problem, try to make triangles, and especially number one trick, make that shape into a 2D dimensional shape. This usually happens when you turn the 2D dimensional shape, when you slice it in half. And this works a lot for like shapes like cylinders and pyramids. And now I'm going to show you guys an example. After this, so the sphere has a surface area of 4 pi r squared, if that's the radius, and the volume is just 4 over 3 times pi times r cubed. And then this is the surface area for the cylinder. This is the volume. This is the surface area for the cone. This is the volume for the cone. All you have to do is memorize these theorems. Most of these you don't have to memorize, but a lot of them you do, like the sphere one. You can't just get it during the test, but the rectangular pyramid, you can get that during the test without knowing the actual theorem. Just come back to this later and memorize them. But let's move on to the next problem. You're not going to fail if you don't know them, but it's sometimes helpful. Well, a right circular cylinder with its diameter equal to its height is inscribed in a right circular cone. The cone has diameter 10 and altitude 12, and the axis of the cylinder and cone coincide. Find the radius of the cylinder. I'm going to give you guys some time to find this out. Remember, cross section, and that's the clue I'm going to give. Now try. Remember, your goal with 3D problems is to turn it into a 2D problem. And that's what you have to do in this problem to make it a very simple problem. So, if a cylinder cone, so if you cut a circular cone in half, you just get a triangle. Like if you look at the front side. So I'm going to draw a triangle now. Wait, no, never mind. I can't draw this over. So the cone has a diameter of 10 and an altitude of 12. If the cone has a diameter of 10 and an altitude of 12, I want you guys to try and find this out. Try this problem out. It's actually a very nice problem. Okay, this is I'm gonna show you guys what to do. So basically, we don't know the radius of the cylinder. Pretend it's just r. So that means the diameter is 2r, but the height is equal to the diameter. That means the height is also 2r. So pretend I have triangle ABC here. We're gonna make some similar triangles. So what is the height? It's just 12 minus 2r. And what is the base? The base is just the diameter of the cylinder, just 2r. And this is equivalent to the ratio of, we're gonna make another similar triangle over. We have another similar triangle, the bigger one, the whole thing. The base, what is the base? 10. And what is the height? 12. Now using this, now we just have to multiply both sides by 10 first. 120 minus 20r. And then you multiply both sides by 2r to cancel this term out. You get equals to 24r. Then this is just simple algebra. You add 20r to both sides, you get 120 equals to 44r. And now all you have to do is divide both sides by 44. So r equals to 120 over 44. You reduce this more, you divide by 4 first, you get 30 over 11. And it says find the radius of the cylinder, and r is just the radius. And that's how we got 30 over 11 as the radius. This is another nice problem. It's a very good one. It's all about 3D dimensional shapes. So triangle ABC with side lengths of 5, 6, and 7 has one vertex on the positive x-axis, one on the positive y-axis, and one on the positive z-axis. Let O be the origin. What is the volume of tetrahedron OABC? I want you guys to try solving this problem. It's a very nice one. Yeah, someone said it's just algebra, and he's right. It is just algebra. There is a lot of algebra in this problem. He's right. Okay, I'm gonna start drawing the diagram. So whenever you a 3D dimensional plane, like we have y and x here. Like if you draw a graph, this is x and this is y. There's something similar for the 3D dimensional shapes also. I'll show you guys how it works. This is how you draw the graph for the 3D dimensional shape. So this is x, this is y, and this is z. Now we have points with side lengths of 5, 6, and 7, a triangle. So we don't care, like pretend this is point. There's this point, there's this point, and then there's this point. And you connect these segments. And this is O, which is the origin. Now we want to find the volume of this figure. However, a lot of these problems have an area which is the same thing. I mean the volume. Sometimes the volume is just the same thing as the pyramid, the same formula. If you find the area of the triangular, the triangular base, if you find that part. So we know the length is 5, this is 6, and this is 7. The answer will be the same whether this is 7, 6, or 5, or this is 5, 6, or 7. The order does not matter. The answer at the end will be the same. So we have to zoom variables. This is A. This whole thing is A. Pretend. This is B, and this is C. We know that these are all 90-degree angles. All three of these angles. So we have A squared plus B squared equals to 36, which is 6 squared. And then over here we have A squared plus C squared equals to 25. And then we have B squared plus C squared equals to 49. Now try solving the problem. Yeah, this is a very nice problem. I want you guys to now solve it. I made the 3 equations that are absolutely needed. Note that the volume of the shape is just B times C, the area of the triangle BC, over 2, like the length, because that's the area of the triangle, times the height A, times 1 over 3, which means the volume is just ABC over 6. So that's what we're looking for. Now, we have 3 variables and 3 equations. This is just a simple algebraic problem now. So A squared plus B squared equals to 36, and you subtract it from this equation. And you get B squared minus C squared equals to 11. But then you have the other equation which involves these variables, so we're going to try to solve the problem now. We want one of the variables to cancel, which is done if we just add both of these equations up. And if you add these equations, you get, there's 1b squared plus 1b squared, 2b squared, Negative c squared plus c squared just cancels out, equals to 11 plus 49, which is 60. Now you divide 2 from both sides, and you get b squared equals to 30. And then you square root both sides, and you get b equals to the square root of 30. Now we can find all of the variables in this shape. Now what is a squared? Now if you substitute this back in here, square root of 30, I mean the square root of square root of 30 is just 30. Then you subtract it from both sides. And then you get a squared equals to 6. And you do the same thing again. That means it's just a is just the square root of 6. So a equals to the square root of 6. Now what is c? You just substitute the variable back here. We'll use a for example. So a squared is just 6. Square root of 6 times square root of 6 is 6. Now you subtract 6 from both sides and you get c squared equals to 19. And then you square root both sides and you get c equals to the square root of 19. So this is what we wanted. Now all we have to do to find the volume is substitute all 3 of those variables back in. And remember, in the beginning we solved the equation to find the volume, which is just all of the side lengths multiplied divided by 6. So we're going to multiply all of these side lengths now. So square root of 30 times 6 times 29 over 6. And that is what we needed. So this is the same thing as 6 to the square root of 5 times 29 over 6. This is just some mathematics. We're not going to spend a lot of time solving this. I'm just have to go through it fast because this is just solving it. There's nothing special in it. So 6 cancel out, and 29 times 5 is just the square root of 145. And that is the answer. And now we're going to do some harder problems. We're going to skip this. You're going to see this on your homework problem because we don't have enough time right now. You'll see this on your homework problem for sure. But we'll do the next problem. I want you guys to solve this problem. I'll read it out first. A machine shop cutting tool has the shape of a notched circle as shown. The radius of the circle is square root of 50. The length of AB is 6. And the length of BC is 2. The angle ABC is a right angle. Find the square of the distance from B to the center of the circle. Now I want you guys to solve this problem. It's a very nice problem. Try solving this. Remember what I said in the beginning? I'm just going to give you guys a clue. Remember, you always connect the center. So pretend the center is O. Well, I'm going to draw this and connect this to OA. And I'm also going to connect this to B. And I'm going to make this height here because we like right triangles. And we know this is square root of 50. And pretend this is point D. Now I want you guys to try solving this. Yeah, someone's right. They said you could use the Pythagorean theorem, and they're perfectly right. There's a lot of computation, but it's all related to the Pythagorean theorem. They're perfectly right. Yeah, try solving. Okay, since this problem is just a lot of Pythagorean theorem, I'm going to show you guys a way to solve this. So, let's assume OD is just X. And then what is AD? We don't know either. This is Y. What is DB? That thing we know. It's just 6 minus Y. Because AB is 6, and the other segment is Y. So you just subtract those, and you get 6 minus Y as this. So I'm just going to draw it here again. So this is 6 minus Y. Now try solving it. Yeah, try solving. It's a very nice problem. Okay. We should connect the radii. We need the radius to be the hypotenuse since it'll make calculation a lot easier. The calculation part. So we're gonna connect OC. And now we have this right triangle also. Pretend this is just E. Now solve it. Now it should be a lot easier to solve. So we know that OD is X. That means EB is also X because it's just a rectangle. And to find OC, to make a Pythagorean relationship, OC squared equals to OE squared plus EC squared. And yes, EC is just the radius. Now we're going to solve the problem. Now what is OC squared? Now OC is just the radius because it's connecting the center to a point on the circumference. And the square of a square root is just the number without the square root. So 50 equals to OE squared. This is 6 minus y as we calculated before because BD equals to OE since this is just a rectangle. And no, EC is not the radius. I mean OC is the radius. So OC squared, that's why we have 50 here. And then EC squared. This is if EB is X and BC is 2. That means EC is just X plus 2 squared. So X plus 2 squared plus OE squared, which is 6 minus y squared. Now this is just a lot of computation, but let's do it. Okay, so basically now if you compute this and simplify, you get 50 equals to x squared plus 4x plus 4 plus 36 plus y squared minus 12y. Now we're going to simplify this. No, before we simplify this, we're going to use the other right triangle, which is triangle OAD. This is just, the side length is x, and the other one is y, so this is just x squared plus y squared equals to 50, and there was nothing much in into this one. So now, these are some, there's a lot of algebra in this. So if we can set these equal to each other because the output at the end is always 50. So we can just set both of these equations to each other. X squared plus y squared equals to x squared plus 4x plus y squared minus 12y plus 4 plus 36, which is 40. Now, the x squared and y squares cancel out, which is good. However, we get 4x. I'm going to write it in the circle now. 4x minus 12y plus 40 equals to 0. Now, the way to solve this problem is to make it so that x equals to 12y minus 40 over 4. And then you have to substitute it back in. There's a lot of computation. There is another simple way which involves trigonometry. However, we are not going to use that method because for the AMC 10, it is not recommended to use trigonometry. However, we could solve this problem now, but it's too much computation and we're running out of time. You can solve it on your own later, but at the end, you'll get the right answer, which is 26. But there's a lot of computation and we don't have enough space or time. So we're going to move on to the next problem. This is a problem number 12 from 1983, the AIM. So it's not going to be that simple. Diameter AB of a circle has a length of a 2-digit integer base 10. Reversing the digits given gives the length of the perpendicular chord CD. The distance from their intersection, point H, to the center O is a positive rational number. Determine the length of AB. Now I'm going to give you guys some time to solve this problem. It's a very nice problem. Try solving it. Yeah, okay, I'm going to lower my mic volume. Someone told me it's too high. Okay, now I lowered it a bit, so it should be more clear. Yeah, this problem is just a lot of algebra. Since we don't have enough time, we're just going to make the equation, and you can solve it on your own later, because solving it will take a long time, because it's a very complicated algebra. Okay, so the equation we get from the problem is simply just, we know AB is a diameter, so it's just a number, and any number, two-digit number, can be represented as 10x plus y. And it's a 2 digits, so we know it's 10x plus y. And the length of chord CD is is reversed, so it's 10y plus x. That means CO is just one of the radii, which is half of AB, so CO is 10x plus y over 2. And then you get CH is half of CD, because if you have a diameter that is perpendicular to a chord, that means the chord actually is divided into 2 equal segments. That's how we get this is 10y plus x over 2. Yeah, and from here you have to use the Pythagorean theorem. There's a lot of computation, and at the end you'll get to something like this. I'm going to make this your homework problem. I'll make the form later, and I'll post it tomorrow. But we do not have enough time to solve this. There's too much computation. You'll have this problem for homework, but I gave you guys the clue to this problem, which is just the Pythagorean theorem. We have to do this problem. This is more important since it's not just algebra. So circles with center A and B have radii 3 and 8 respectively. A common internal tangent intersects the circles at AC and D respectively. Lines AB and CD intersect at E, and AE equals to 5. What is CD? Now, this problem is just similar triangles. Pretend if we connect CB and AD, we get a right triangle. Because if you connect a tangent line to the radius of the circle, you always make a 90-degree angle. So we know this is a 90-degree angle, and the base is 3, and the hypotenuse is 4. So this is just a 3, 4, 5 relationship. So DE is 4. Similarly here, we know the base is just 8. And we don't know the length of this segment. Pretend this is C. We don't know that length, which is X. So we can use similar triangles here and pretend we take the hypotenuse over the shorter base, which is 3, which is equivalent to the hypotenuse of this triangle, which is 8 plus X over the shorter base 8. Now we're going to solve this equation to get X. So you get 40 equals to 24 plus 3X. And 3x equals to 16. X equals to 16 over 3. And we want CD. That means all we have to do now is add up 16 over 3 and 8 to get the hypotenuse, and then we can use the Pythagorean theorem to get CE. So 16 over 3 squared is just 256 over 9 plus 8 squared, which is 64. Minus 8 squared, which is 64. And we want this all we want the denominator to be n, so it's easier to simplify this. Actually, I want you guys to try solving this problem now. I want you guys to try just try solving this. Oh, sorry, I forgot to write this down. The actual length of EB, if you put this in the Pythagorean theorem, is 1600 over 9, which equals to CB, which is 64, and which is the same thing as 576 over 9, plus pretend EC is just x squared. Now if you subtract 1600 with 576, you get 1024 over 9 equals to x squared. Now 1024 is just 32 times 32, and 9 is just 3 times 3. So we have 32 over 3. And now you add both of these up, and you get 32 over 3 plus 4, which is the same thing as 12 over 3. And if you add these up, you get 44 over 3 as the length of CD. So now we're going to move on to the next problem. I mean, not problem. I'm going to show you guys some concepts, which they're not used that often, but if you see a problem, then it can be faster to use these concepts. So an inscribed angle basically is half of the arc that it forms. Pretend AC is 1/4. I mean, like it's like, pretend this is like 60 or 1/6 of the entire circumference, which means it's like 60 degrees. That means angle B is 30 degrees. It's exactly half. And a line tangent, I've said this many times in the video, but a line tangent to a circle is perpendicular to the radius drawn to the point tangency. This is a very important theorem that you guys should know no matter what for these contests. So let's move on to the next problem. No, we're going to skip this since we don't have enough time. We're going to go to the challenge problem, which is AME problem 14 from one of the years, and it's a very hard problem. Actually, it's not that hard, but it involves a lot of computation. In the adjoining figure, with radii 8 and 6 that are drawn apart with their centers 12 units apart at P, one of the points of intersection is drawn such that the chord QP and PR have equal length. Find the square of the length of QP. Now I want you guys to try solving this problem. I'll give you guys 3 minutes. 3 minutes, yeah. Okay, try solving. It's a nice problem. There are many different ways to solve this problem, but the easiest one is similar triangles. So make similar triangles. Yeah, remember to draw similar triangles. A lot of these problems that have are about circles are all about similar triangles, and not just similar triangles, just normal triangles also. So draw triangles inside. Yeah, and this is our last problem. Okay, we're gonna solve this problem. It seems like people are leaving, so we'll just solve this. So pretend the center of this bigger circle is A, and then the radius is 8 and 6. So if you connect Q and A, you just make a radii, which is 8. And then you also connect BR, pretend this is B, and you connect BR, you get this is 6. Now to get similar triangles, we first need to make this into a right triangle. So hopefully, maybe we can make some relationships here. And then if you draw a segment all the way here, pretend this is M and this is N. And using AA similarity, we see that MRB, angle MRB is in both of the triangles, which means that we can simply use angle similarity and then prove these triangles similar. We already know they're similar. We don't really have to prove them. Okay, so what does this mean? Well, this means that the ratio of the hypotenuse, which is 6 in the first case, and the base, pretend this is x, 6 over x. No, we know that the hypotenuse of the other triangle is 18, which is just 3 times the whole triangle, the hypotenuse of the smaller triangle. So if the base is x, then the other base is just 3x. And now, try to solve this problem now, using the fact that I just told you, the information. Okay, it seems like we're running out of time, so I'm just going to explain the solution. Remember, there's this theorem that states, basically we know that if the altitude, like we see that this is 90 degrees, which means it divides a chord in half. Because if you draw a line from the center of the circle to a chord and it forms a 90-degree angle, which means it's perpendicular, that means that angle is 90 degrees and it divides the chord in half. That is the theorem we need to use in the triangle. So if MR is Y, we know PM is Y. But it also says that these two chords are equal, and this one also divides it, also makes a 90-degree angle from the radius. So this is also Y, and this is also Y. Now try solving the problem. Okay, whatever, I'll just explain it. So basically, x squared plus y squared equals to 36 because of the Pythagorean theorem. And then we have 3x plus 3y equals to 18 squared. 18 squared. 3x squared plus 3y squared. So if you put this back, if you like 9x squared plus 9y squared equals to 18 squared, which is just 18 times 18, which is 324. Now try solving the problem. Yeah, okay, just try solving this. It's a very nice problem. Oh, we also have another equation because we have another right triangle here. And the other equation is 9x squared plus y squared equals to 64. Now it should be more clear how to solve it. So if you take this first equation and the third equation, and you subtract the third equation, and you subtract the first equation from the third equation, the y squareds cancel. And you get 8x squared equals to 28. Because 64 minus 36 is just 28. Now x squared equals to 28 over 8, which is, you first reduce it, which you get 7 over 2, and then, which means this is just the square root of 7, the square root of 7 over 2 square rooted, which is the length of x. Now the problem should be doable. You first rationalize this, so you get square root of 14 over 2, because you multiply both sides by square root of 2, to make the denominator just an integer. Now try solving the problem. Okay, I'll just explain it. So all you have to do in the problem is now substitute y squared back. If this is x, we need y. And then, so we'll substitute it into this equation. It seems the easiest to do. So square root of 14 squared is just 14 over 2 squared, which is 4, plus y squared equals to 36, which is the same thing as y squared equals to 130 over 4 after you subtract 36 with 14 over 4 and you square root that. And after you square root that, that is the length of half of the chord. That means the full chord is just 2 times this, which is the square root of 130. And that is QP. However, we want to find the square of that length. And if you square a square root, you just get the length without the square root, which is 130. And then now we cracked out in AME problem 14 using similar triangles, which shows the power of drawing these similar triangles inside circles. So thank you for watching, and please don't forget to like, share, and subscribe to our channel. Oh, someone's asking why we got 130, and the reason is that we made similar triangles, and we know that x squared plus y squared in this triangle is 36, which is this equation, and this is 3y, the length of this, and this is 3x, so this is 9x squared plus 9y squared equals to 324, but we didn't need to use this equation. Instead, we used this one. We know the base is 3x, and this Qn is y, because if you draw a line from a radius from the center and it is perpendicular to the chord, that means it divides the chord in half. That's why if NP is y, that means QN is also y, because it divides it into two congruent segments. So then we use 9x squared plus y squared equals to 64. And then we subtracted it from the first equation, and after substituting, that's how we got 130. And now, thank you for watching, and our next class is next week.